Section 8.2 is about hypothesis testing for a single proportion. The first big block of stuff on this page is about the requirements or conditions necessary for inference. So ideally, you would want your sample data to come from a simple random sample. That's always the way that it's phrased. Realistically, as long as you have a representative sample, you would be good to go for that first point. So it doesn't have to be a simple random sample. It could be one of those other sampling methods that involves randomization that we talked about earlier in the course. Those would actually be fine, but usually you don't end up with a sample that's that ornate, right? That's that complicated. Like you don't end up with like a stratified random sample or anything like that, right? Here it's a test for a single proportion, so you're just going to have one single group that's not differentiated at all. So you could have other stuff, but you'd probably need a more complicated test. So for a test for a single proportion, a simple random sample, realistically, that's the best way to go. Then the next thing is conditions for a binomial distribution being satisfied. So why is that in there? Because the underlying distribution that allows you to use the central limit theorem, as long as you have a big enough sample size, it's a binomial. Because for any kind of proportion, if you look at it on an individual basis, like for individuals in the sample, whatever the question happens to be that would eventually formulate a proportion, for every individual it's a yes or a no, right? Whether it's an opinion poll or it's the proportion of people who have side effects to a medication or something like that, it's always either it happens or it doesn't. So those are two options, binomial. That's why that shows up. The biggest thing is having independent trials. That was a big thing when we did binomial probabilities, and that's the most important one here. But if you have a simple random sample, that takes care of independence. So really, the big ones for our purposes are going to be the first and third, because we're going to kind of get the second one for free if we've got the first one. The third one is the big one. This is really the one that you have to check, that your sample size is large enough to apply the central limit theorem. If you don't have that, there are other things that you can do, but we're not going to cover them. There are ways that you can use simulation instead of the central limit theorem. They're actually in our book. If you look up like bootstrapping, I guess really the bootstrap is for a confidence interval, but you can make adjustments to that and basically simulate a p-value. Although we're not really going to get into that. We're just going to deal with if the sample size is big enough. So the sample size is large enough if you get these two things to happen. If n times p0 and n times 1 minus p0 are both at least 5, and the p0, that's the number that's in the null hypothesis. I guess really it's in both hypotheses, but you tend to think of it as being in the null where it's phrased as p equals number, right? So it would be p equals p0. Whatever that number is, that's your p0. Okay. So then when you're testing a claim about a proportion, what the null hypothesis looks like probably isn't going to be news. Those show up in section 8.1 as well, where it's going to be p, not p hat, since the test needs to be about a parameter, so you got to have a p in there, equal to some number, and that some number is your p0. Then as long as your sample size is big enough to apply the central limit theorem, then the sampling distribution of p hat would be approximately normal. And it can be approximated by normal distribution with a mean of p and p0, the assumed value of p from the null hypothesis, and then the standard deviation of that root. And then there's the test statistic. Our book uses a z for this. I always just say TS for the test statistic. If you want to use the big Z, you can use the big Z. But with using Z's, I always kind of thought that like you have the big Z for the test statistic and then the little z for the critical value, and they look too similar to each other. Like if you're going to use the rejection region approach, then you end up talking about, well, is big Z less than little z, or is big Z bigger than little z? And I don't know. I would rather not have the notation look so similar for things that you're comparing that are different quantities. But it is actually an accepted convention to use the capital Z. It's not like it's our book's fault. That's the way that it's been for decades. But I always write TS just so that way they seem like they're more differentiated in my brain, I guess. So what we're going to use to figure out the p-value or the rejection region would be the standard normal distribution. That's the way we were doing it in 8.1. That's the way we're going to do it now. So everything with a proportion, standard normal. Confidence interval, use the standard normal. Hypothesis test, use the standard normal. And then The easiest way to do a hypothesis test is to make StatCrunch do the whole thing. Now, if you're going to use the rejection region approach, or if a homework question asks you to, right? I mean, I guess that's really where that decision gets made. If you're going to use the rejection region approach, you're going to need the test statistic, although that does show up in the output. Although that way, if you want to do it the long way, you could. It doesn't really take that long. But if you're going to use the p-value approach, you could just make StatCrunch do the whole thing, and this is how you would do it. So on the stat button in that menu that shows up, you want to go to proportion stats, then one sample. And then for everything that we're going to do, realistically, it's going to be this. It's going to be with summary. With data would be if you had the raw data, but we always have a sample proportion, and that's a summary value. Right? The raw data would be a column of yeses and nos for the individuals in the sample. And we never have that. It's always, well, we had 145 people say this out of 180. So then p-hat's 145 over 180, and that's a summary value. So we're always going to have with summary. And then this also matters because if you're using the rejection region approach, you need the test statistic. So if you would rather duck around doing the computation, and I don't blame you, because if you do the computation, you have to use this root that's up here. And it's a little bit involved to get that into a calculator, unless you've got a calculator that can handle like a whole string of text in one line. But even then, you kind of still have to be vigilant about parentheses and stuff. If you would rather not do that, then as long as you know where the test statistic is, you don't really have to. You'd have to figure out what the rejection region was, but then you could make StatCrunch figure out the test statistic for you. So anyway, onwards to the examples. We'll do them the short way and then we'll do them the long way. I figured it was worth doing the same ones twice just to kind of get that comparison in there. But there's not a lot of variation from one to another, other than maybe with what kind of inequality you've got in the alternative. Like if you have a one-sided alternative versus a two-sided alternative, those are a little bit different. But other than that, I mean, procedurally, not a whole lot's going to change. All right, so this first example, and this is real. I don't have the actual article anymore, but I'm sure I could find it if I had to. So, at the University of North Florida, 2 business professors conducted a study regarding college students' perceptions of grading systems. And a questionnaire was given to 251 randomly selected students. 150 said they prefer whole letter grades, so just A, B, C, and so forth, with no pluses and minuses. And then 101 preferred plus or minus grading, so to have minuses and pluses in there. It's rare that you actually see the A+. Apparently there are schools that do that. I went to a school that had the pluses and minuses, and we didn't have an A+, though. We also didn't have a D or D+, now that I'm thinking about it. It went C-, then D, then E. Anyway, we're going to do a hypothesis test to see if this indicates that the proportion of college students who prefer whole letter grading is greater than 0.5. Right? So that's what we're looking for evidence of. So P, which I guess I can do this in another color. I'll do it in maroon. So the proportion of college students who prefer whole letter grading, that is P. Right? Because that's the college students as in all college students, not the 251 in the sample. So if we were going to write out the hypotheses, then, and I know I said this in 8.1, but it's worth stressing again, I think it's easier to write out the alternative first, because that's got the inequality in it. And that's the thing we got to be kind of alert for, because you can have different inequalities, right? So greater than 0.5. All right. So then that's what we're looking for evidence of. So the alternative should be that P is greater than 0.5, which would mean then that the null is that P is equal to 0.5. Let's see. Then the other thing that we've got is the sample proportion, which I guess I can put this in a different color. Brown. So the sample proportion, that's, let's see, so if it's for whole letter grading, 150 preferred that. So 150 over 251. And then we should be able to use StatCrunch to get our p-value. So that's going to be our next step. There we go. All right, so StatCrunch. And this should do it. So if we go to StatCrunch, then we want to go to Stat, and then we want to go to Proportion Stats, and then one sample, and then with summary. And then the number of successes and number of observations, that's for the sample proportion. So ours is 150 over 251. And then that is our null, p equals 0.5. The alternative just needs to have a greater than in it, since that's what we had for our alternative. And then compute, and there we go. The p-value is 0.001. So that's the thing that we were looking for. And notice if you want it, the test statistic is right next to it. So the test statistic is about 3.093 if you want that. But then the p-value is 0.001. All right. So our p-value was 0.001. And also, because we're going to have the comparison later where we do the whole thing out, the test statistic is 3.093. And this, I'm just going to put like in a cloud. Because like here, you don't need it. Right now, this is just like a thought bubble that we're going to save for later because we're going to need it in, I think it's on the next page, actually. So we're going to need it in a few minutes. Then make a decision about the null. Well, this part, you just have to compare the p-value to your significance level and figure out which one's smaller. So the p-value is 0.001. The significance level is 0.05, right? So 0.001, that is less than 0.05. So the p-value is less than alpha. And so then your two possible decisions are either that you're going to reject the null or you're not going to reject the null. So when the p-value is less than alpha, that's when you have a statistically significant result and you do reject the null. So our decision would be that the null should be rejected. And then for a formal conclusion, maybe something like there's enough evidence or there's sufficient evidence to conclude what's in the alternative. That's basically what you want to say. So I'll just say that there is sufficient evidence to conclude that, and then the alternative is actually there in the wording. It starts with the part in the maroon brackets. So I'm going to copy it verbatim and just say that the proportion of college students who prefer whole letter grading is greater than 0.5. And that's it. So there's sufficient evidence or enough evidence to conclude what's in our alternative hypothesis. Since we had a nice tiny p-value, so we could reject the null and say, okay, it looks like the alternative's probably right. And look at how little computation we did there, since basically we made StatCrunch do all of it. And then in number 2, we're going to do the same exact thing. So you can probably anticipate what's going to happen in number 2. Since there's a one-sided alternative in number 1, you'd think there's probably a two-sided alternative here, and you would be absolutely right because of this right here. Different than 82%. That's what we're looking for evidence of. So different than doesn't specify a direction, so we can't specify a direction either, and we're going to need a not equal to in the alternative hypothesis. So let's see what we got up toward the top. According to Myers-Briggs estimates, about 82% of college student government leaders are extroverts. And then we had a random sample of 193 of them who were given the Myers-Briggs personality preference test, and 149 were found to be extroverts. Okay, that gives us our p-hat. right? 149 out of 193 in the sample. But then, let's see, setting up the hypotheses. So I guess here we would have, so once again, I'm going to get the alternative first. And I would say there that what we're looking for evidence of is that P is not equal to 0.82. Right? Different than 82% in proportion form. That would be that the population proportion is different than 0.82. And then the null would be that it's equal to 0.82. All right. And then the other thing that we can pull out of here, and it's actually in the first paragraph, is what our sample proportion is. And so it's 149 out of 193. So P hat is 149 divided by 193, whatever that is. I guess it's bigger than 75%, but other than that, or bigger than 0.75, but other than that, I can't get too far off the top of my head. Then we're going to go to StatCrunch and have StatCrunch do its thing. So stat, proportion stats, one sample with summary, and let's see, we have 149 out of 193 for our sample proportion. Then the null is that P equals 0.82, and we do have a two-sided alternative, so we're all set, and we just have to go click compute, and there we go. We're going to get a p-value of 0.0827, and then our test statistic right next to it is negative 1.735. All right, so I guess I'll use the same color scheme I used up above. So in StatCrunch, we got a p-value of 0.0827, and then in our thought bubble, we're going to put our test statistic of negative 1.735. So we want to be thinking about that for when we do it the long way in a few minutes. All right, so then make a decision, formal conclusion, just like with the last one. Okay, this time the p-value is bigger than the significance level because it's the same alpha. Right at the end of the wording up toward the top, use significance level alpha equal to 0.05. So we're comparing the 0.05 to 0.0827, but the 0.0827 is bigger. So this time the p-value is greater than alpha, greater than the significance level. And when that happens, we don't have a statistically significant result, and that means we should not reject the null. So the null should not be rejected. Okay, and then as far as the conclusion goes, this time there is not enough evidence, or there's insufficient evidence. I guess I'll write it that way. Since I said sufficient last time, I'll say insufficient here. So there's not enough evidence or insufficient evidence to conclude what's in the alternative. So insufficient evidence to conclude that. And then the alternative is actually written out in words in the second paragraph. So I'm just going to copy it verbatim, that the proportion, I guess I could say it as population proportion, but I'll just write as proportion of extroverts among college student government leaders is different than 0.82. All right, so I guess that's about that. If you're going to use StatCrunch to do the whole thing, that would do it. Right? I mean, you've still got to set up your hypotheses, right? You can't make StatCrunch do that. So you still have to comb through the wording, figure out what kind of inequality you need in the alternative hypothesis, figure out what the numerical value is that goes in the two hypotheses, and I guess identify your sample proportion. But if you can do all those things right, you can make StatCrunch grind out all the computation for you. The other 2 pages in here are what if you didn't make StatCrunch do everything. So just for reference's sake, what if you did do all of it? Or I guess as much as you could without, I mean, eventually you have to resort to technology to figure out the probabilities, right? Like to use the standard normal to get the p-value. You can't really do that by hand. So let's see. For this one, with the grades, our hypotheses were that we had a null that p equals 0.5, and we had an alternative that p is greater than 0.5. The sampling distribution, so let's see. Assuming the null is true, right, so assuming that p really is 0.5, we do have a big enough sample size. So we can say that the shape would be approximately normal. Right, so this really is the central limit theorem step right here. So I'm going to put CLT in parentheses. And the reason this works is because we need n times p0 and n times 1 minus p0 to both be at least 5. Here they're way bigger than that. They're actually both 125.5, because in this case, n times p0 would be 251 times 0.5, right? Because 0.5 is our p0, it's the values in the null hypothesis. This is 125.5. But if p0 is 0.5, so is 1 minus p0. So n times 1 minus p0. If you go through and do it, you also get 125.5. And 125.5 is definitely bigger than 5, right? So right, we need to be at least 5, and we got way over that bar. All right, other than that, we know it's going to be approximately normal, but the things that define a normal distribution are the mean and the standard deviation. So then the mean would be p0, which, and this is the assuming the null hypothesis is true part, you'd have 0.5. And then the standard deviation would be the square root of p0 times 1 minus p0 over n. So then that's going to be the square root of 0.5 times 1 minus 0.5 over 251, which to 4 places works out to be about 0.03. That's a terrible looking 3. It's about 0.316. So 0.316. And then if you want to compute the test statistic, that would be the next thing. So the test statistic ends up being, so it's p hat minus p0 over that root. Right, so the square root of p0 times 1 minus p0 all over n. And what you would end up with is that you would have, well, I guess you have to get p hat. It's about 0.598 if you round to 3 places. So where am I getting the 598? I guess I should write this up in the corner in maybe a different color. This is where I got some empty space up here. It's the 150 over 251 written as a decimal. So that works out to be about 0.598. So that's where that comes from. And so we're going to have that minus the 0.5 and then divided by 0.0316 if you use the rounded off version in the denominator, and you get about 3.101, which is a little bit different than what we had. If you go back to the last page when we had StatCrunch do it, it had 3.093. The 3.093 is actually better because that's what you get with no rounding. So I'm going to put that in parentheses here. You do get 3.093 with no rounding. Like if you don't round off any intermediate steps, which I did here because I have that square root in the denominator rounded off. But if you don't do that, if you just do that computation like within a calculator and then have 0.098 divided by previous answer, you'll get 3.093 because then you're not rounding intermediate steps. But then let's see, the p-value and or rejection region. All right, so if we're going to get the p-value, I guess that'll be the first picture. And then rejection region will be the second picture. So then the distribution that's here that you would have to use would be the standard normal. So then I'm going to be using normal, mean 0, standard deviation of 1. Same thing for the rejection region, actually. But then for the p-value, if it's standard normal, it's going to be centered at 0. And then our test statistic is 3.101, which is way out in the tail. And then everything past that. So the right tail is going to be our p-value because we had a greater than in the alternative hypothesis. So then the p-value should be a right tail. So that thing that I have shaded in, that is the p-value. And I guess at this point you would have to resort to either a calculator or StatCrunch anyway. But you would just use the standard normal distribution to get that probability. So calculators, normal. It's set up for standard normal. I want a tail going the other way, and I want the cutoff to be 3.101. And look, what we got was 0.001 before when we used StatCrunch to do everything. Here we're getting 0.00096. Pretty close, right? So let's see. Then our p-value ends up being 0.00096. All right. So then what about with the rejection region? If we did it that way instead, right? So you wouldn't do both of these. You would really just do one or the other. But if we did the rejection region, so this is still standard normal, still going to be centered at 0. But then our rejection region, and I guess I'll do this in a different color. So it's all going to be in the right tail because we have a greater than the alternative hypothesis. And then alpha is 0.05. So that's the probability that has to go into that tail. So in that tail we have alpha, which is 0.05. So that tail is our rejection region. And then we just need the cutoff. And then we can go to StatCrunch to get that part. Or if you have a calculator that has preloaded distributions, it'll have the normal and you'll be able to do it that way. But let's see here. I don't want that specified. I just want 0.05 in the tail. And if I have 0.05 in the tail, the cutoff has to be 1.645. So that's what I need. All right, so then 1.645 for that cutoff. And then our test statistic was 3.101, and that's farther out into the tail, right? Like it's someplace out there, like it's bigger than 1.645. So the test statistic was 3.101. That would have to be in the rejection region, right? It's bigger than 1.645, so therefore it's out in that maroon colored tail. All right, so then the decision, I mean, we're going to get the same decision that we had before, right? Because either you could say, well, the p-value is less than alpha, which it is, or the test statistic is in the rejection region, and those are the cases where you would reject the null. So either approach that you took, you would end up saying that the null should be rejected. All right, then the other one, if we do the other one the long way, the other one being the one about the Myers-Briggs test. So we had a null that p was equal to 0.82 versus an alternative that p is not equal to 0.82. And then since I need to write it in somewhere, let's see, change color. I think I did it in maroon last time. P hat is going to be 149 over 193, which is roughly 0.772. So we're going to need that. And then, let's see, do we have a big enough sample size? Yeah. If you multiplied everything out, you're going to be fine. And I'll write out what they are in a second. But it is big enough so you can say that the shape will be approximately normal, which is the central limit theorem part. And let's see, so then if you did the multiplication, n times p0 would be, so n is 193, so it's 193 times 0.82, which is, it's about 158.26. Okay, that's big enough, right? It just had to be at least 5, so we're good there. The other one's actually going to be smaller, because if p0 is 0.82, 1 minus p0 is 0.18. So n times 1 minus p0 here is really the one that we have to watch out for, I guess. But we're going to have 193 times 0.18, which is about 34.74. But we're good, right? Because that number and that number, so both are greater than or equal to 5. And that's the thing that we're looking for, right? That's when we have a big enough n to where we can say, well, now we can apply the central limit theorem, and we can say that the sampling distribution is approximately normal. All right, other stuff, just like with the last one, the mean would be p0, which here is 0.82. And then the standard deviation would be that root, so the square root of p0 times 1 minus p0 over n. And if I sub in, that's going to be 0.82 times 0.18 over n, which is 193. And this works out to be roughly 0.0277, rounded to 4 places. Then with the test statistic, if we want to go ahead and compute that, so the test statistic will be, so it's p hat minus p, or minus p0, use the notation the book uses, over the square root of p0 times 1 minus p0 over n. And there are a couple of things rounded here because p hat's rounded and so is the root, but we should get something pretty close to what we had a couple pages ago. So we'll have 0.772 minus 0.82 over 0.0277. And what that works out to is about negative 1.733. And what you get with no rounding is negative 1.735. So negative 1.735 with no rounding. And if I go back up, so I'm just going to scroll up for a second just to point at there. Look at the in the middle of the screen inside the maroon cloud. Test statistic, negative 1.735. All right, that was what we had when we made StatCrunch do it. And that's what you'll get with no rounding. And again, ours is slightly different because there are things that are rounded off a little bit because that root and the denominator is rounded off, and then p hat is also rounded off. All right, so then once again, we can get the p-value and the rejection region. So just like with the last one, might as well make the p-value on the left, rejection region on the right. Use the same order that they're showing up in the wording. And this involves proportions, so we're going to use a standard normal. So again, standard normal in either approach. And then for the p-value, if it's a standard normal, it's going to be centered at 0. Our test statistic is negative 1.733. So I guess that's about maybe there. And we'd have this left tail, but we have a two-sided alternative. So what we have now with just this tail is what you'd have if you had a less than in the alternative hypothesis. But we also need the tail on the other side. And starting the same distance away from 0, it would have to start at positive 1.733, and we'll need that. So that's the one thing, if you're going to do all the steps yourself with the two-sided alternative, just make sure you watch out for that, that you do have to manufacture that second tail because the test statistic, it's only one number. It can only by itself give you one tail, but you can figure it out, right? I mean, it's a standard normal, it's centered at 0. So the tail, it's the same size on the other side. Just negate your test statistic, and that'll give you the other one. All right, so then we got to figure out our p-value. Let's see, if you're going to do it this way, I guess you could either do it, you could do it with the between, and say you want between negative 1.733 and positive 1.733, and then 1 minus the between would do it. So like 1 minus 0.9169. So our p-value is 1 minus 0.9169, which is 0.0831, which is slightly different than what we had when we made StatCrunch do everything. I think when StatCrunch did everything, it was 0.827, but that's just because the test statistic is slightly different because of rounding. We're still going to get the same conclusion. And then with the rejection region, if you were going to do that, all right, so we're still centered at 0 since this is a standard normal. And alpha is 0.05, but you've got to split the rejection region in half because we've got a two-sided alternative. So I guess I can write this up here. If alpha is 0.05, then that means we have to put alpha over 2, which is 0.025 in each tail. So that's what I'm going to end up with. I'm going to have a left tail over here as part of the rejection region, and this is going to have 0.025 in it. And then I'm going to have a right tail over here that also has a 0.025 in it. And then we just need the cutoff. All right, well, there are a couple of different ways you could do it. I guess you could say, what if I wanted a 0.95 in the middle? That would give you the right answer. So it is 1.96 and negative 1.96. Another way you could do it is just specify one of the tails. So if I went back to the standard setup and I just said I want a 0.025 in that tail, 1.96 again, right? So either way should work. And then I guess whatever way we're doing it, what we're going to end up with is on the right tail 1.96 and on the left tail it's negative 1.96. And then our test statistic is negative 1.733, so that's not quite into that left tail. Right? It's on the left side of the picture since it's less than 0, but it doesn't quite make it. So if it's not in that left tail, it's not going to be in the rejection region here, right? It's in between the two pieces. It's in between those two tails. So not in the rejection region, so you would not reject the null. So either way, right? Either we could say, well, the p-value is bigger than alpha, which it is here, since alpha is 0.05 and 0.0831 is bigger, or the test statistic is not in the rejection region. Either way, these are the situations where the null is not rejected, right? If it's not in the rejection region, you don't reject it. But also if the p-value is bigger than alpha, you don't have a statistically significant result, so you don't reject it. And once again, you would not do both of these in practice. It's overkill because you would always get the same conclusion from the rejection region approach that you would from the p-value approach. So you would really just do one of them, right? If you're going to get the same thing either way, you would just do it once rather than doing it twice, right? Doing it the second time effectively creates extra work if you're actually going through one of these. I did both of them here just to get every possible path in here. But really you would just do one or the other. Although I think for a lot of these, really what you'll end up doing is having StatCrunch do most of it, which I think is fine. Then that way you don't have to worry about, do I have enough parentheses in this thing that I put in my calculator so the order of operations is going to work right? You don't have to do any of that stuff. And you can pull the test statistic out of the output from StatCrunch. So even though that's set up to use the p-value approach, you could also use the rejection region approach, although I suppose you have to figure out the cutoffs for the rejection region. But that's usually not too bad, right? You just use the standard normal, you specify what goes in the tail, and you're pretty much there. But I think that would cover everything for section 8.2.